everyone, I'm Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. Today we are going to discuss question bank related to band theory of solids and of course introduction to semiconductors. Coming to band theory of solids, where we talk about how energy bands have originated, and based on energy band diagram, how we can classify solids into conductors, insulators and semiconductors. And coming to semiconductors, here we are going to discuss what exactly are semiconductors, how many types we have, and then how to explain them based on their energy level diagram and to calculate their carrier concentration, and in the end, one of the best application of semiconductors, that is Hall effector. So today we are going to discuss all those questions related to these topics. So moving further, first we are going to discuss short type answers. Okay, so coming to first question, define block theorem. So we know that if we take a crystal, in that crystal, if we consider regular arrangement of atoms, then instead of saying crystal to be regular arrangement of atoms, we talk about array of positive ions and its valence electrons moving freely inside the crystal. So if I try to draw crystal structure, then I will say that I have regular arrangement of positive ions, and in this array of positive ions, I have valence electrons moving freely. So these valence electrons, they are moving freely throughout this crystal structure. Okay, and what we are going to observe here is, depending upon position of electron inside this crystal, I have considered one-dimensional crystal lattice, and based on position of electron in this crystal lattice, its potential is going to vary. And what you are going to understand here is, if we consider two adjacent positive ions, if A is intra-ionic spacing between these two adjacent positive ions, then its potential with respect to x is distance of electron from any positive ion, then you will observe that it is going to be periodic with respect to A. A is distance between two adjacent positive ions. So, and how the potential is going to vary? So in this case, suppose if you consider two adjacent positive ions, and what you will observe here is, if electron is exactly in the middle between two adjacent positive ions, its potential will be maximum, and whereas it has got this maximum value, and when this electron is approaching positive ion, its potential is going to drop to 0. And this variation of potential with its position, it is going to be uniform throughout the entire crystal structure. So when we have such electron moving in a periodic potential, then Bloch, he has given one notation or one representation for wave function associated with electron moving in a periodic potential, and that wave function, it is given as psi of x is equal to u of x e to the power of ikx. Now coming to this particular wave function associated with electron moving in a periodic potential, as you can see, there are two terms. E to the power of ikx, it represents plane wave equation, which is modulated by one more periodic function. So this u of x, which is called as modulating function, it has same periodicity as periodicity of potential, that is nothing but intra-ionic spacing A. Okay, so what generally, according to Bloch theorem, so wave functions associated with electron moving in a periodic potential, it is given by a plane wave equation which is modulated by a periodic function whose periodicity is same as potential of electron. So that is nothing but Bloch theorem. Then coming to second question, define a metallic solid and draw its band diagram to explain its electronic behavior. So if you consider a metal, we know that it's a good conductor, and if we try to explain them based on their energy band diagram, we know that in case of metals, there is no forbidden energy gap. So lower permitted band is valence band, higher permitted band is conduction band, and in case of metals, we have overlapping of valence band and conduction band, and there is no forbidden energy band. So you will have free flow of electrons from valence band to conduction band. That's why they are good conductors. There are plenty of free electrons available for conduction. So this is about the metallic solid. And then next we have classify crystalline solids based on band theory. So based on band theory or based on this energy band diagram, we have three types of solids. First type, of course, we have insulators, and then second type we have conductors, and coming to third one we have semiconductors. So it is purely based on width of forbidden energy gap. The next question, define a semiconductor and draw its band diagram to explain its electronic behavior. So if you consider semiconductors, so based on energy band diagram, these semiconductors, they are defined as materials in which width of forbidden energy gap, which is given as Eg, is small. So width of forbidden energy gap is very small, so that if we supply energy, generally they are insulators, their valence band is completely filled at T is equal to 0 kelvins. And if we supply energy, then electron which is there in the valence band, it absorbs that energy and it jumps across the forbidden band and it goes to conduction band. So as a result, we have hole in valence band and electron generated in conduction band. So this is about semiconductors. Then coming to insulators, in insulators, what we'll observe here is when we are talking in terms of width of forbidden energy gap will be very much wide. So here width of forbidden energy gap is wide. So what do you mean by having very wide forbidden energy gap? It means that in order to make a valence electron, conduction electron, we need to supply large amount of energy. Suppose if we take glass, in case of glass, this forbidden energy gap, it is around 10 electron volts. And if we supply that much of energy, then material, it is going to get destroyed. So that's why, because there is no availability of free electrons or any type of charge carriers, so that's why here conduction will be very, very less in case of insulators. Then of course define a conductor. So because the metals are good conductors, already we defined metal, energy band diagram of a metal. So as I said, there is no forbidden energy gap. So valence band and conduction band will overlap. It means that we don't have to supply energy in order to make valence electron take part in conduction. Simply we'll have flow of electrons from valence band to conduction band. Next one is explain the classification of semiconductors based on variation of conductivity in terms of temperature and doping. So coming to semiconductors, basically they are of two types. So generally they are taken as, if we consider first type of classification, here we have first type intrinsic semiconductors and then second type are extrinsic semiconductors. So if you take intrinsic semiconductors, here we'll increase their conductivity by going to high temperatures. But whereas in case of extrinsic semiconductors, even at low temperatures, intrinsic semiconductors, they are made conductors. How? By adding different dopants. And based on what type of dopants we are adding, again extrinsic semiconductors, they are of two types. One is P type and second one is N type. In P type, we are going to add travalent impurities. In N type, we are going to add pentavalent impurities. Then, summarize your understanding of an intrinsic semiconductor and give an example. So, coming to intrinsic semiconductor, so best examples of intrinsic semiconductor are silicon and germanium. If we take silicon, and this silicon, it belongs to group 4 elements. So the silicon atom, it is going to have 4 valence electrons. And these 4 valence electrons, they will take part in covalent bond formation with adjacent intrinsic atoms. So this silicon, it is going to form 4 covalent bonds with its adjacent silicon atoms. As all electrons are taking part in covalent bond formation, there are no free electrons. That's why they are basically insulators. But if we increase temperature, then all these covalent bonds will break. So what do you mean by breaking of covalent bonds? It is nothing but jumping of electron from valence band to conduction band. And when one electron jumps from valence band to conduction band, there will be generation of one electron hole pair. So depending upon number of transitions from valence band to conduction band, we'll have so many number of pairs of electron and holes. So that's why what you will observe here is when we increase temperature, these intrinsic semiconductors, they'll start acting as conductors. And of course, two best examples for intrinsic semiconductors are silicon and germanium. Then next, ninth question. Define the term doping and why do we need to dope an intrinsic semiconductor? So doping, it is the process in which we add certain foreign atoms or impurities to an intrinsic semiconductor. And what is our main aim? Main aim is to increase conductivity or increase number of charge carriers at low temperatures. Generally, in order to make intrinsic semiconductor conductor, we have to go for high temperatures. But by doping, what we are doing, we are trying to increase number of charge carriers as well as electrical conductivity at low temperatures. So that is our main purpose behind doping an intrinsic semiconductor. Then next, what is an extrinsic semiconductor and how it is more useful than intrinsic semiconductor? We know that if we take intrinsic semiconductor like silicon and germanium, and if we dope them with foreign impurities, like it can belong to group 3 element or it may belong to group 5 element, based on doping, we are increasing number of charge carriers. And this impure semiconductor is nothing but extrinsic semiconductor. And how is it going to help? As we have seen that when we add dopants, these dopants, they are going to donate charge carriers to intrinsic atoms. Suppose if we add pentavalent impurity to intrinsic semiconductor, it is going to donate electrons to the conduction band of intrinsic semiconductor. So without going to high temperatures, we are able to get electrons in the conduction band. Whereas if we dope travalent impurities, then we are increasing number of holes in the valence band without any involvement of conduction band. So all this increase in charge carriers, it is taking place at low temperatures. The next one, write the expressions for carrier concentration of electrons and holes in intrinsic semiconductor. So carrier concentration, if you consider concentration of electrons, it is given by symbol N, and coming to its formula, it is given by 2 into 2 pi me star kt by h square whole to the power of 3 by 2 exponential EF minus EC by kt. So this is the formula for number of electrons in conduction band of intrinsic semiconductor. And coming to number of holes in valence band, it is given by 2 pi mh star kt by h square whole to the power of 3 by 2 exponential EV minus EF by kt. And of course, what is EF here? EF, it is Fermi energy level, and of course Me star and Mh star are effective mass of electrons and holes. Then write expression for intrinsic carrier concentration. Now intrinsic carrier concentration, it is represented as Ni, and generally what we'll do in order to get intrinsic carrier concentration, we are going to multiply expression for density of electrons in conduction band and density of holes in valence band, and if we do it, then we end up having our intrinsic carrier concentration as 2 into 2 pi kt by h square whole to the power of 3 by 2 into me star mh star whole to the power of 3 by 4 exponential of minus Eg by 2 kt. And what is Eg here? Eg is forbidden energy gap, and how this forbidden energy gap is given, it is taken as difference of bottommost energy level of conduction band to the topmost energy level of valence band. So this is the expression for intrinsic carrier concentration. Now give the expression for Fermi level in intrinsic semiconductors. So here, when we are talking about Fermi energy level, generally, what we'll say here is, of course, in case of intrinsic semiconductor, this Fermi energy level, it is taken as EC plus EV by 2 plus 3 by 2 kt ln of ratio of effective mass of hole to the effective mass of electron. So this is the expression for Fermi level in intrinsic semiconductors. Then define Fermi energy or Fermi level. Now coming to Fermi energy level, its location, it is going to be different for different types of semiconductors, and also it will be different for different temperatures. And if we try to define Fermi energy level at T is equal to 0 kelvins, then we'll define Fermi energy level as the boundary energy level. So it is the boundary energy level which is going to separate filled energy states and unfilled energy states. As you can see, below Fermi energy level, all the energy states are filled with electron, and above the Fermi energy level, above Fermi energy level, all the energy levels are empty. So that's why T is equal to 0 kelvins. Fermi energy level is the boundary energy level which is going to separate filled and unfilled energy state. And this definition, it is going to hold good only at temperature 0 kelvins. Then write Fermi distribution function for electrons in metals. So this Fermi distribution function, it is given as f of E. And what does it indicate? It indicates probability of an electron occupying a particular energy level, and it is given as 1 by 1 plus exponential E minus EF by kT. This is the expression for Fermi-Dirac distribution function. Now, show an expression for carrier concentration of electrons in p-type semiconductors, and of course carrier concentration in n-type semiconductors. If you consider n-type semiconductors, then what we'll observe here is carrier concentration. Actually, when we are talking about p-type semiconductors, we talk in terms of holes, and when we talk about n-type semiconductors, we talk about electrons. And if we try to take expression for density of holes in p-type semiconductors, so it is taken as, so here it is written as PP. So what is PP? It is density of holes. P represents density of holes in p-type semiconductor, and it is given as 2Na whole to the power of half, where Na is acceptor concentration. That is number of acceptor atoms added per unit volume of the material. 2Na whole to the power of half exponential. So here in this case, of course, it 2Na half, then 2 pi star kT by h square whole to the power of 3 by 2 exponential. Here we are going to have Ea minus Ec by 2 kT. So this is the expression for density of holes and electrons in case of n-type and p-type semiconductors. Now here, of course, when we are deriving expression for them, suppose if you are talking about carrier concentration of holes in p-type semiconductor, so what we are going to do first, we are going to consider density of holes in p-type semiconductor, which is given as 2 into 2 pi mh star kT by h square whole to the power of 3 by 2 exponential EV minus EF by kT. And this one, of course, it is approximately equal to density of ionized acceptors. So what do you mean by density of ionized acceptors? So in this case, it is taken as F of EA. And we know that F of EA, so it is written as exponent, of course, Na into F of EA. So this is Na into exponential of so in this case it is EA minus EF by kT. So here we have this is the density of holes in p-type semiconductor, and this is density of ionized acceptors. And in order to get expression for carrier concentration, that is holes in p-type semiconductor, we are going to multiply these two expressions. So if we multiply, then this PP square is nothing but, of course, this is P, and this is of course NaF of A. So if we have to multiply these two expressions, then we end up having it as 2Na into 2 pi mh star kT by h square whole to the power of 3 by 2 exponential. Okay, and if we consider these two expressions here in this case, so this is EF minus EA by kT. So EF will get cancelled, so it will become EV minus EA by kT. Okay, and if we take square root, so we end up having it as 2Na whole to the power of half, and this will become 3 by 4, and this will become EV minus EA by 2 kT. So if we try to write this expression clearly, then here we are going to observe that coming to density of holes in p-type semiconductor. So it is given as pp is equal to 2na whole to the power of half into 2 pi m h star kt by h square whole to the power of 3 by 4 exponential EV minus EA by 2 kT. So this is the expression for carrier concentration of holes in p-type semiconductor, where Na is of course it is acceptor concentration, how many number of acceptor atoms are added per unit volume, and of course mh star is effective mass of hole, and EA it is called as acceptor energy level, which will be very close to valence band of intrinsic semiconductor. EB is topmost energy level of valence band. Of course, K is Boltzmann constant and T is absolute temperature. And similarly, if we want to write density of electrons or carrier concentration in N-type semiconductor, then it is represented as Nn. N stands for density of electrons in N-type semiconductors. So it is given as 2Nd whole to the power of half. Here Nd is donor concentration, number of donor atoms per unit volume of the material, into 2 pi me star kt by h square whole to the power of 3 by 4 exponential ed minus ec by kt. And what is ed here? Ed is donor energy level, which is very close to conduction band. So these are the expressions in case of p-type and n-type semiconductors. Now give the statement of Hall effect. So what is Hall effect? So if we consider Hall effect, in case of Hall effect, what we'll do, we take a small slab of either conductor or semiconductor. So in this case, what we are going to do, so if we are placing this semiconductor with its length along the x-axis, and then what we are going to do, we are going to pass current I along its length, that is along the x-axis, and then I am going to apply magnetic field along the y-axis, that is perpendicular to the direction of flow of current. Then what we are going to observe here is in a direction perpendicular to both x and y axis, that is along the z axis, we are going to have charge separation, and because charge separation, there will be formation of voltage. So a voltage will be developed across this material. So this particular phenomena, it is called as Hall effect. So how we are going to keep it in statement? So the phenomena of production of Hall voltage across a material which is subjected to current and magnetic field perpendicular to each other. Or we can also give this statement as when magnetic field is applied perpendicular to a current carrying conductor or semiconductor, then the production of Hall voltage in a direction perpendicular to both current and magnetic field is nothing but Hall effect. And this particular Hall effect, it is going to have many applications. It helps us to find mobility, conductivity, as well as we can know what is the nature of semiconductor using this phenomena. Then next, draw the diagram showing charge carrier concentration or charge carrier excitation at T is equal to 0 kelvins and at T greater than 0 kelvins for N-type and P-type semiconductors. So we know that at T is equal to 0 kelvins, suppose if we take these materials, now as we know that suppose if I am considering N-type semiconductor and if I take energy band diagram of N-type semiconductor, we'll observe that of course when we are talking in terms of conduction band and valence band, here we are going to have one more energy level which is donor energy level. And what you are going to observe here is here at T is equal to 0 kelvins, this donor energy level, it is filled with electrons, whereas if I increase temperature, that is T greater than 0 kelvins, then what we are going to observe that here we have transition of electrons from donor energy level to the conduction band of intrinsic semiconductor. And what happens in donor energy level, because it is giving its electron to conduction band of intrinsic semiconductor, so it will become positively ionized. So this is the energy band diagram of N-type semiconductor. Now coming to P-type semiconductor, if we take P-type semiconductor, of course here we have conduction band and we have valence band. and there is one more energy level known as the acceptor energy level, which is close to valence band. And what we'll observe here is at T is equal to 0 kelvins, we have electrons in the valence band. And once we increase temperature, if you go to temperature greater than 0 kelvins, then we have transition of electrons from valence band to the acceptor energy level. Then we have holes being generated in the valence band. And what about the travelent impurities or acceptor atoms that are added? They will become negatively ionized because they are accepting electrons from the valence band of intrinsic semiconductor. So that's why here in this case majority charge carriers are holes and here majority charge carriers are electrons. Now coming to last short question. Relate the properties of N-type and P-type semiconductors. So when we are trying to figure out properties, first point we have to talk in terms of the doping. So in N-type, we'll dope them with pentavalent impurities which belong to group 5. And in P-type, we are going to dope them with trivalent impurities which belong to third group elements. And second thing is, if we take N-type semiconductors, majority charge carriers are electrons, whereas in P-type semiconductors, majority charge carriers are holes. And coming to N-type semiconductors, of course, whatever impurities we are adding, they are called as donor impurities. And in P-type, they are called as acceptor impurities because they are accepting electrons from the valence band of semiconductors. And so we have taken different types of short answers, and then next we are going to discuss about long answer questions. Now coming to first question. So here we have to talk about Bloch's theorem. And of course, motion of electron in a periodic potential. Already I have discussed, if we take a one-dimensional crystal, then how we are going to define this one-dimensional crystal. It is nothing but array of positive ions. And this array of positive ions, we have valence electrons moving freely inside the crystal. And if we take A as intra-ionic spacing, that is distance between two adjacent positive ions, then what we are going to understand here is, if we take x direction and these are our positive ions, then what we are going to see is, depending upon the position of electron between two adjacent positive ions, its potential is going to change. And how its potential is going to change? It is maximum at the center when it is exactly in middle between two adjacent positive ions, and when it is approaching positive ions, its potential is dropping to 0, and will have same type of variation of potential for every two adjacent positive ions separated by distance a. So that's why we call such potential to be a periodic potential whose periodicity is intra-ionic spacing a. And if we consider such electron moving in a periodic potential, then according to Bloch theorem, their eigenfunctions or energy functions, they are given as plane wave equation, which are modulated by one periodic function whose periodicity is same as periodicity of potential of electron. So this is our Bloch's theorem. Then coming to second one, show that energy spectrum of an electron contains allowed energy bands separated by forbidden bands using Kronnig Penney model. So for this, first we have to consider motion of electron in a periodic potential. So for that, again, what we are going to do, we are going to construct potential boxes which are separated by potential barriers. And if we consider this region as 0, and if this is taken as A, then the other region will take it as minus B. Here we are taking variation of potential of electron which is moving in a periodic potential. Here, in this case, when electron is between the region 0 to A, its potential is constant and will take it to be 0. Whereas here, of course, here we have positive ions. So when electron is exactly between two adjacent positive ions, its potential is maximum. That maximum potential is taken as V0. And when that electron is approaching a positive ion, its potential is going to drop to 0. So when we take such variation of potential, then we end up having potential boxes, and inside the potential box, electron is a free electron whose potential is 0. And when electron is approaching positive ion, then it is separated by potential barrier because it is suffering a very high potential which is V0. So that's why it is not able to come out of these potential boxes. And if we take and if we make use of Schrodinger's wave equation, then we end up having very important equation as P by alpha A sin alpha A plus cos alpha A is equal to cos Ka. And what is P here? P it is called as potential barrier strength, which is given as mv naught AB by h cross square. M is mass of electron, V naught is this height of potential barrier, and of course A is this width of potential box, and B is width of the potential barrier, and of course h cross it is given by as h by 2 pi, where h is Planck's constant, whose value is 6.6 into 10 power of minus 34 joule second. So using this equation we are going to plot one curve. So what we'll do in this curve, so we are going to take left hand side of this equation. So in this case we have plotted left hand side. What is left hand side of this equation? That is P by alpha A sin alpha A plus cos alpha A, and I'll assume my P value to be infinity. So if we take it, and of course on x-axis if we take alpha A, then what we'll observe here is, because if we take this left hand side, on right hand side we have cos value, and this cos value it is bounded between plus 1 and minus 1, so automatically even left hand side is also, it should also get bonded between plus 1 and minus 1. So when we keep on substituting different values of alpha A, then what we'll observe here is only for certain particular values of alpha, this left hand side of this equation it falls between plus 1 and minus 1. And those values of alpha, they are shown by the shaded regions. Whereas if you consider this unshaded region, these are those values of alpha for which left hand side of this equation is going beyond plus 1 and minus 1. So it means that the shaded region it is formed with permitted values of alpha, unshaded region with unpermitted values of alpha, and we know that alpha square it is related to energy. That's why shaded region it will give you allowed energy bands, unshaded regions will give you forbidden energy bands. This shows how energy bands, allowed energy bands and forbidden energy bands have come into existence. Now explain origin of energy band formation. So when we talk about origin of energy band formation, here what we have to say here is, suppose if we are able to isolate an atom, then in that case we are going to have discrete energy levels. Okay, so if suppose if I am able to take single atom, then it will have only one energy level, whereas if I take two atoms together, then splitting of energy levels will take place, and here you are going to have two energy levels. Whereas if you consider a solid which consists of many number of atoms, so when you are considering group of atoms, so in this case you will have many energy levels which are very closely spaced to each other, and such a set of closely spaced energy levels is nothing but energy band. An energy band concept comes only if we consider group of atoms which are present only inside a solid. Whereas if we take isolated atom, then we have to talk only about discrete energy levels. Then compare intrinsic and extrinsic semiconductors based on their energy band diagram. So simply I am going to draw energy band diagram here. Suppose if we talk about intrinsic semiconductors, then we are taking in terms of conduction band and valence band, and at high temperatures we have transition of electron from valence band to conduction band. This is for intrinsic semiconductors, and whereas for n-type semiconductors, if we consider, then we are going to have one more energy level which is called as donor energy level, and then of course this is valence band and conduction band. And here we have transition of electrons from donor energy level. Then this donor impurities will become positively ionized, and we have electrons in the conduction band. Then coming to p-type, here we have valence band. So this is our valence band. This is the conduction band. We have acceptor energy level, and here transition of electron takes place from valence band to acceptor energy level, leaving holes in the valence band. And here in this case, this acceptor impurities will become negatively ionized. Then obtain an expression for carrier concentration of N-type semiconductor, as I have shown you, like I have discussed before also. First, what we'll do, we'll take expression for density of holes in conduction band, whose expression is given as 2 into 2 pi me star kt by h square whole to the power of 3 by 2 exponential ef minus ec by kt, and then we are going to multiply it with density of ionized donors, which is given as n d into 1 minus f of ed, and this will become approximately equal to nd exponential of ed minus ef by kt. And if we multiply these two expressions and if we take square root, we'll get expression for carrier concentration, and that expression, it is given as 2 nd 2 pi mh star kt 2 pi mh star kt by h square whole to the power of 3 by 2 exponential 3 by 4. So here exponential, it will become ed minus ec by 2 kt. So similarly for holes also we'll do it. And what is the expression we are going to get for p-type semiconductor? It is taken as 2 Na whole to the power of half into 2 pi mh star kt by h square whole to the power of 3 by 4 exponential. Here in this case, it will be EV minus EA by 2 kt. Now, next is finding intrinsic carrier concentration. So here what we have to do, first we have to consider density of electrons in the conduction band, and which is given as n is equal to 2 into 2 pi mh star kt by h square whole to the power of 3 by 2 exponential ef minus ec by kt. And similarly we have to derive expression for density of holes, which is given as 2 into 2 pi m. So if it is me star, then it is mh star kt by h square whole to the power of 3 by 2 exponential ev minus ef by kt. And in order to find the intrinsic carrier concentration, we are going to multiply these two expressions and then we are going to take square root. Then we are going to get expression for carrier concentration. And in order to get Fermi levels, here we have to take n is equal to p. And if we rearrange the terms, then we end up having expression for Fermi energy level as Ec plus Ev by 2 plus 3 kt by 4 ln mh star by me star, and at t is equal to 0 kelvins, or if we assume that if effective mass of electron is equal to effective mass of hole, then this will vanish, and then we'll have our Fermi energy level to be exactly middle of conduction band and valence band. And explain the dependence of Fermi level on carrier concentration and temperature in extrinsic semiconductors. So in this case, what we have to do, so if we are talking about n-type semiconductors, then with respect to energy, if you are going to take here, suppose on x-axis we'll take temperature, on y-axis we'll take energy level, and we know that in case of n-type semiconductor, here we are talking about n-type semiconductor, we have conduction band and then we have valence band, and this is our, in this case, this one is Fermi energy level, intrinsic Fermi energy level in intrinsic semiconductor, which is middle of conduction band and valence band. And at t is equal to 0 kelvins, where is the Fermi level? If this is the donor energy level, then Fermi energy level is exactly middle of donor energy level and conduction band. And as temperature increases, this Fermi energy level gradually lowers towards the intrinsic Fermi level. And if you want to talk in terms of donor concentration, then we'll observe that as donor concentration increases, then this is for higher donor concentration, which is 10 to the power of 24 atoms per meter cube. This is for lower donor concentration, which is 10 to the power of 21 atoms per meter cube. So you'll observe that lowering of Fermi level from Ed plus Ec by 2 to the intrinsic Fermi level, which is Ec plus E by 2, it will be fast in case of lower doped material compared to highly doped material. And similarly, if we talk about p-type semiconductor, So if we take p-type semiconductor, here in this case when we plot Fermi level, so here we have temperature, and this is with respect to energy, and this is our valence band, and this is conduction band, and of course this is our intrinsic Fermi energy level, and here we have acceptor energy level, and at T is equal to 0 kelvins, this is the Fermi energy level. As temperature increases, it gradually raises towards the intrinsic Fermi level, and that raising of Fermi level, it will be slow in case of highly doped material, and this one is for 10 to the power of 21. So now Hall effect, already I have explained about Hall effect, and we have to obtain expression for Hall coefficient. So in order to get expression for Hall coefficient, so what we are going to do, here we'll say that, of course when we are talking about Hall effect, we'll take a piece of semiconductor and we'll apply current in this direction, magnetic field in this direction, along the z direction we have separation of charges. So we have generation of Hall voltage, and here charge carriers inside this material, they are subjected to two forces. So first we'll take Hall electric force, and then we'll take of course first due to magnetic field, it's a deflecting force, it is given as Q into Vd cross B, and then Hall electric force, it is given as QEH. And what we'll observe here is at equilibrium both these forces will get balanced. So in this case EH in terms of amplitude, it will become VdB, and here in this case if we take this drift velocity and current density, then what we'll observe here is drift velocity, it is given as J by NE. N is carrier concentration. So if we substitute here, this will become JB by NE. Then EH by JB, it is equal to 1 by NE, and it is taken as Hall coefficient RH. And of course, just now I have taken graphical representation of Kronnig Penney model, where we'll take this expression P by alpha A sin alpha A plus cos alpha A is equal to cos Ka. We'll take left hand side of this expression on y-axis, and we'll take alpha A on x-axis, and we'll get shaded and unshaded regions. Then moving further, classification of materials, same based on their energy band diagram. So if we take conductors, there is no forbidden energy gap, and if we take insulators, very wide forbidden energy gap, and if you take insulators, very small forbidden energy gap. So we have to explain based on the width of forbidden energy gap. And derive expression. So in order to derive expression for density of electrons in conduction band of intrinsic semiconductor, then what we have to do, we have to take density of energy states Z of E, D, and also we have to take density of holes in small energy interval, and we have to take Fermi-Dirac distribution function. And what you will observe here is this density of electrons in conduction band, it is given as density of energy states into Fermi-Dirac distribution function. And then after that, in order to get density of electrons in entire conduction band, we are going to of course we have to integrate this value, and that integration limits will be lowermost band of conduction band is EC, and topmost it is taken as infinity. And if we do it, then we'll get expression for electron concentration. And for holes also we are going to follow same thing, but in this case limits of integration will be, upper limit will be EV and lower limit will be minus infinity. I think already we have discussed about energy level diagram at T is equal to 0 kelvins, T greater than 0 kelvins, and we have discussed about N-type and P-type based on their doping and energy band diagram, and we have discussed variation of Fermi energy level with the dopant concentration as well as temperature in both N-type and P-type semiconductors. And then coming to uses of Hall effect, it is used to find nature of semiconductor, whether it is P-type or N-type, because Hall coefficient value is positive if taken semiconductor is P-type, and if it is N-type, then Hall coefficient is negative. So we can make out even carrier concentration, mobility, conductivity, so using this Hall effect, and as well as expression for Hall coefficient. Then coming to part C, analytical question, find carrier concentration. So in this case, we were given band gap, okay, and because it is given in electron volts, we'll convert it into joules. We were given temperature and we are supposed to find carrier concentration. We know formula for carrier concentration, 2 into 2 pi kT by h square whole to the power of 3 by 2 me star mh star whole to the power of 3 by 4 exponential of minus Eg by 2 kT. So all parameters are given, and also you are given effective mass of electron to be equal to effective mass of hole, and this is equal to rest mass of electron. And what is the value of rest mass of electron? 9.1 into 10 power of minus 31 kilograms. And what is the value of Boltzmann constant? 1.38 into 10 power of minus 23 joule per Kelvin. And of course we were given value of Eg as well as temperature. And coming to this problem, at what temperature would Fermi level be shifted by 15% from middle of forbidden energy gap? So for this problem, what we have to do here is, first we have to take expression for Fermi energy level. This expression, it is given as EC plus EV by 2 plus 3 kT by 4 ln mh star by m star. This is the expression for Fermi energy level. And at T is equal to 0 kelvins, EF is equal to EC plus EV by 2. But at T is equal to 0 kelvins, where is our Fermi energy level? Exactly middle. So if I take band diagram, so if this is conduction band and if this is valence band, at T is equal to 0 kelvins, where is our Fermi level? Exactly middle of conduction band and valence band. So it means that, and what is the value of band gap given? So Eg is given as 1.2 electron volts. So this location is, so when we talk about this one, so this will be EV plus 0.6 electron volts. So this is EV plus 0.6 electron volts will give us Fermi energy level at T is equal to 0 kelvins. Whereas if we go for other temperature, it increases by 15%. So if you go for 15%, then what we'll observe here is, so this will become EV plus 0.75 electron volts. Okay, so this is equal to EC plus EV by 2 plus 3 kT by 4 ln of, we were given that effective mass of hole is 5 times, so this will become ln 5. And what is this value? We have to take from this, and if we rearrange the terms, then we'll get expression for temperature. And to find the position of Fermi energy level, we are going to take this particular formula. And here, based on conductivity and mobility, so if we consider all these equations, then we'll observe that we are going to make use of expression for Hall coefficient as 1 by Ne. And here, it is also given by formula EH by JB. And we know that EH, it is given as VH by D, where D is the width of the slab. And current density, it is given as current per cross-sectional area into B. And this particular area, it is written as thickness into width. So we have one more formula for Hall coefficient as VHT by current into B. So making use of this formula as well as this formula, we can find the carrier concentration. Also, we can find if Hall voltage is given, we can find Hall coefficient. If Hall coefficient is given, we can find Hall voltage. And also we can find mobility and conductivity also. So mobility, it is given as Ne. So here in this case, it is given when we are talking about the conductivity and mobility. So relation between conductivity and mobility is Ne mu. So using this relation, we can find mobility or conductivity. And if you want to express in terms of Hall coefficient, then mu, it is given as sigma by Ne, and 1 by Nv is Rh. So it is Rh into sigma. So using this formula, we can find the mobility of charge carriers, we can find conductivity, and also we can find density. So we are going to make use of these two formulas in order to solve remaining 8 questions. So with this, I'm going to finish my video here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.